Okay. After weeks and weeks of looking at rather dull, boring grey slides with code on, I thought we needed a bit of light and a bit of get our heads into a bigger space maybe, and just so I thought I'd talk about spatiotemporal databases today for a change, because I find something I find fascinating, and it's I think it's quite a fast-moving area in certain ways. So not surprisingly, many problems in the world, if not almost all of them, are temporal problems as well as spatial problems. A whole list of stuff, you know, those various applications, vehicles moving, transport solutions, pollution movements, climate change, urban development patterns, demographic change, crime, you know, just about everything in the world has a temporal component, just like it has a spatial component. And to deal with that temporal component, we need to, unsurprisingly, develop databases that can store, manage, manipulate temporal data. And just a couple of little definitions there. A temporal database is simply a relational database that has time included in it so that it allows you to manage attributes that change through time. And a spatiotemporal database is simply a database that allows us to do space and time together. And they generally, in fact, if not entirely, extensions of spatial database management systems, extensions of relational database management systems. So you add time in on top of your temporal model, on top of your relational model or your spatial relational model. And personally, I'm coming to the opinion that this makes time, which seems a simpler thing than space because it's linear and it has other characteristics which we'll explore in a minute, makes it really difficult to manage because it's an add-on. It's not integral to the development of certainly spatiotemporal databases. The time is something that we bolt on afterwards as much as having it integrated into the whole system design. And I'm starting to think, well, maybe we need to think about how we reorganize databases, or maybe I'm just ignorant and don't know about the developments in certain areas of temporal databases. Okay, and just to note there that at any point in time, a temporal database is a standard relational database for a spatial relational database. So so we've got four sections in the lecture. So the first of all is a nice bit of a hand-wavy kind of section where we'll think about what is time. And if you've got any thoughts about time that I haven't included in my list, then I'd be interested to discuss them. So these are sort of things. Over my years, I've worked with a number of temporal databases, temporal data sets, and my research is embedded in time because it's about evolution and landscape change. So I have an interest in time, and it's just things that I've come across about time that I think are quite interesting, and it's kind of the domain side of time, if you like. Then short little section on how we measure time, just like it's important to understand the basics about how you measure things in space. It's also important, understandably, to understand how we measure things in time. And then how time is stored, what the data models, the data types that exist in relational database technologies for dealing with time. And then finally, I've got a little section on how time is implemented in ArcGIS. And this seems to be quite rapidly moving. So there's a number of tools, new tools arriving in 10.3. At the moment, the university serves 10.2 out, but I've got 10.3 loaded on a machine in my office. And there's new tools for managing time in 10.3, which is quite interesting. There may even be ArcGIS tools to do with time that I haven't managed to find yesterday. So there might be a whole load of tools that I'm not going to mention simply because I don't know about them. But if you find some interesting stuff, then feed it back to me. Okay, so what is time? I don't know whether this guy knows what time is or not. Maybe he does. I don't know. Maybe he's the expert. Okay, so first thing is time seems simple, but we've understood it through time in different ways. So how you understand time depends on where you are historically. And that's true about everything in life. We are all products of our own time. And this just highlights some of the major developments in concepts of time through history. So Aristotle, I'm no expert on some of this stuff, but Aristotle, so what was it, Greek, so Greek 3,000 years ago, 2,500 years ago, was when he considered time, considered that time was to do with motion. Without motion, you could have no time, because time is about change. We'll get into that in a minute. So Aristotle, in the ancient times, the thought of time was very connected to the idea of motion. Without motion, you had no time. Newton, in Newton's theory, time is separate from space. So Newton's theory of how planets orbit the sun and things like that. In the calculations, space is dealt in one way, time is dealt in another way. It's a separate dimension from space, something different from space. However, by the late 19th century and early 20th century, the idea that time was in fact another similar dimension like space took on. So it was no longer separate as in Newton, but it became the ideas started to develop that it was in fact a dimension like space that you could move around in, that you had a certain perhaps control over, and it's very similar to another spatial dimension. It is the fourth dimension. And some of the sort of emergent sort of cultural things that developed from that were things like the ideas of, to a certain extent, spiritualism and Cubism in art. Spiritualism, where you could connect with spirits across the divide in time. Cubism, I'm not an art historian, but breaking down the ideas, the ideas of the rigidity of features in space and in time. So there's different ways. Also very interesting from this time is if you've ever read or seen the film of Flatland, which is a story of a whole load of shapes who live in a two-dimensional world, who one day met a sphere arrives in the two-dimensional world, and it's the story of the two-dimensional shapes trying to understand what this strange new visitor to their world is, which includes, and to understand it, they have to understand that they live in a world of two dimensions, but reality has three dimensions. So, changing views on time, and then of course, just over 100 years ago, it's almost, I think it was 1908, general relativity, I can never remember, it was 1908, 1916, Einstein brought space and time together into a coherent idea where where space is relative to time. I'm not a physicist, obviously, but the idea here that I want you to take is that there have been these different views of time, different epistemological views of time throughout history, and we're still working on it. We still don't really know what time is, particularly, and it varies depending on what domain you're in. So let's just have a little quick tour through these things that I think are relevant to time. You know, some of them are not directly relevant to geography, but they're things about time so that makes me understand what time actually is. So first of all, as I say, it's not really relevant to most GIS, but we don't really know. We think time had a beginning, if we believe in the Big Bang, but there are alternative views of how the universe, steady state views of the universe. So we think it had a beginning. Now, depending on the fate of the universe, it may or may not have an end, depending on whether the universe collapses on itself, maintains a steady state, or the present view of the universe seems to be we're accelerating towards a sort of long, slow, cold death. And even if we believe that time began here, perhaps there was some other. So we don't even know whether time really has a beginning or an end for a start. But we do know, as I say, time is change, and Aristotle, early Aristotle connected very closely time with change. And there are lots of different types of change. There's change in existence. We're all born and we all die. There's an element of splitting and coalescing in existence. My children are a product of me and my wife, and things like that. Species evolve through time. Lakes, as lake levels go down, they split from one lake into two lakes. So there is things not only begin and end, they can split apart, they can merge together. So there's changes in existence, there's changing in the attributes of things. Here's Hurricane Andrew, and we've got various dots, and the colour is showing the intensity of the hurricane at the particular time. So it's changing in attribute as it moves through space and time. It's also changing in location. So the centre of the storm is moving. It's perhaps growing, contracting. There is flow around the hurricane centre. And that rate of change can vary. Some things are effectively instant, things like earthquakes, from the human perspective. Maybe if you're interested in the actual event itself and the sequence of seismic waves and how they affect the land surface, then perhaps they're in fact gradual events. Again, it's to do with how you're discretizing the world, how you're taking the world apart. So some changes are effectively abrupt, instant. Many changes are gradual. Time is change. Time is also essential to understand causality. Without time, you have no cause. You cannot determine causes and effects. And cause and effect is, of course, is the result, to a certain extent, is the result, requires potentially an arrow of time, occurs within the linearity, the arrow of time. A cause cannot happen before an effect. An effect can't happen before a cause. Or maybe they can. But. So cause and effect results in the arrow of time. And we think generally, I do, as time being linear. 5 minutes today is the same as 5 minutes tomorrow, or 5 minutes yesterday. And we have a monototic, we can think of time as a linear process. Here we've got, this is an old chart, the history of various empires, and we've got equal line divisions. The vertical lines are time. Here's the Roman Empire. Vertically we've got different geographical regions. So we've got, there's Germany, the Belgians, Britain, various other parts of Europe, and then the colour blocks are showing the space and time occupied by various empires through time. But there's very much, in this diagram, a feeling of ordering, a feeling of everything is uniform, everything trundles forward, perhaps towards progress, who knows. That's perhaps something else. I should have had a slide, the sort of, are we moving towards progress? Are we moving towards greater complexity? Anyway, so linear, time is often thought of as linear. But within that linearity, there is often directional change. This is a graph of what's called the Living Planet Index, which is collated by the Zoological Society in London. It's an index of the health of populations of plants and animals across the planet. It started in 1970, and basically what they do is they collect abundance records for species all around the planet, and they say, okay, in 1970 there were maybe 100 and, I don't know, take a figure off the top, 100,000 elephants. And then as the years go by, there are less and less elephants, less and less seals, less and less plants, less and less songbirds. And this is a measure of how much biodiversity has declined at the planetary scale through time. And as we can see, since the mid-1970s, there's been almost a linear decrease in the overall number of animals on the planet. And we have, I mean, it's shocking when you look at these figures, but 30% of animal life on the planet has been destroyed in 40 years. Shocking figures. Anyway, but the idea here is not, I'm not trying, is that we've got this kind of relatively linear trend. It doesn't, but we've got trends in these data, directional change in data. But it's not all just change, linear change. It's not all linear progress. The world is full of cycles as well. Time itself is not cyclic, but many processes on the planet are cyclic in time because of the rotation of the planet on a daily basis, around the sun on a yearly basis. But also there are other effects at different scales, other drivers at different scales of cycles in time. So this is very topical at the moment. This is the Southern Oscillation Index, which I'm no expert on, but it's a measure of temperature difference across the Pacific, and it's basically the primary index for the El Nino, La Nina effect. So we're presently at one of these extremes, or approaching one of the extremes in the El Nino effects. There are floodings in, I think, in South America. I always get it a bit muddled up what's going on where, but there's extreme weather conditions around the Pacific Rim as a result of these El Nino effects. And we can see that there is a cyclic behavior to these temporal cycles in the El Nino effect. And these are driven, I believe, they're on a sort of 3 to 7 year cycle, and I think this is to do with circulation of water through the Pacific Basin that actually drives these cyclic changes. So it's not that time is cyclic, it is that the world has cyclic drivers in it. So here's a few examples of these, as well as that El Nino, which is on the scale of years. So ice ages, glacial interglacial stages, are driven by cycles in the Earth's orbit, and eccentricities in the orbit at various scales, including 100,000 years and 400,000 years. So the primary driver of ice ages over the last 2 million years has been these eccentricities in the Earth's orbit. There's also a question as to why the ice ages started 2 million years ago in the first place, which is to do with the positioning of the continents on the planet and how they, particularly how they cut off the Arctic Ocean. That's believed to be the main driver of the beginning of ice ages. Human movements. There's cycles at various scales determined by both our diurnal behaviour. We get up in the morning, most of us come to work, go home at night. The weekly structure, the arbitrary weekly structure we impose on our lives, the weekends versus the work days. Yearly patterns to do with holidays, to do with winter, summer, things like that. And then we have other things like the internally driven Arctic hare lynx cycle, which you may have heard of, which is driven by predators and prey every about 3 years. Basically, you've got lots of Arctic hares, breed like mad, loads of Arctic hares across the Arctic. Then the foxes start eating the hares like mad, get lots of foxes, very few hares, foxes die off, it all starts again. These are internally driven temporal cycles. So they may be very important in the patterns that you see in your geographic data. Having said that, linear patterns, cyclic patterns, the reality is quite often a lot dirtier, and things happen at different scales and at different times. So this is a graph that attempts to put the temperature of planet Earth over the last 500 million years. So we're going back to the Precambrian here. It's on a sort of loggish scale up to the present day. here's the last 10,000 years. This is the end of the last glaciation. And we can see that we've got cycles at different scales, at different wavelengths, at different times in history. We've got trends, what appear to be relatively linear trends at certain times. We've got what maybe appear to be sort of semi-random at times. So the patterns that you see in your data will be dependent on the sort of temporal scale that you're looking at to a certain degree. And just because something is happening today in a particular way doesn't mean that it's going to happen tomorrow in that way or in the past in that way. Space and time are intimately linked. Through, all right, you can say through physics with Einstein and indeed Newton and things like that, but biologically, geographically, they are very closely linked. This is an example of what's called a, if I remember correctly, a Hallström diagram after a Norwegian ocean scientist, I think it was, in the 1960s, who first drew these kinds of scale diagrams. I think they're wonderful diagrams. What they are is diagrams of the scale, so the logs, in this case, the spatial scale, in this case, log kilometers. So 0 here is 1 kilometer scale, a 1 would be 10 kilometers, a 2 would be 100 kilometer scales. Negative, you're going down to sub-kilometer scales, so -1 is the scale of 10 meters. And on this diagram by Peterson et al., they've overlaid the processes that operate, the dominant processes at various spatial and temporal scales. And as you can see, hopefully, that there is a correlation, not surprisingly in many ways, between space and time. It takes time for processes to move across large spaces, unless they're very rapid. So there tends to be quite a strong correlation between spatial and temporal scales. So if we're talking about food choice of these, this is in the boreal forest of North America, I believe. So if we're talking about food choice between moose and beaver, we're looking at relatively small spatial temporal scales. But if we're looking at changes over yearly fire regimes, home ranges, dispersal and migration of animals, we're looking at larger spatial temporal scales. If anybody's looking for a project, well, says, I've got a collection of these, and one day I want somebody to digitize these in the GIS and look for correlations between these space-time scales, between all these different biological and human processes, to see whether there are particular scales at which lots of different processes change how we look at them or how we discretize space. So I thought these could actually be digitized into GIS and then do an overlay kind of analysis onto these space-time diagrams. I thought that would be an interesting thing to do one day. Okay, what else about time? If you're interested in psychology and perception, because you might get in a job where you have to do GIS of perception. This is why I'm telling you about these things. These are the kinds of applications, these sorts of ideas and things you might need to incorporate into some kind of application at a future date, as well as just simply for the interest. So perception of time. Time, we perceive, as human beings, time in different ways depending on our circumstances. So here's an example. You're at school, you're somewhere dull, time seems to slow down. If you're somewhere interesting, something having fun, it can seem like time moves really fast. It can also happen under different circumstances. My closest shave with death was a bike accident when I was about 18. I still remember the slow motion video in my head as I went head over heels over the back of the car, lay in the middle of the dual carriageway with the trucks going past my head a foot away from my head. I still remember that vividly, the slow motion effect of it as my perception of time changed because of my circumstance. And this is not just human beings, the whole of the biological world operates in different times. Why is it so hard to swat a fly? It's because a fly world, the world of the fly is roughly 6.8, 7 times faster than that of a human, perceptually. That's why they're so good at getting out the way, because you're coming at them like this. Slow motion, 7 times slower than you think you are, and they can get out the way very quickly. So if you're interested in the behavior of animals and organisms, and indeed people, of course, you may want to take into account the perception of time as well as the reality of what actual time it is. And this behavior at an individual level comes out in group level as well. So here's a graph of finishing times for marathon runners. It's quite interesting. Here we are, 3 hours, 4 hours, 5 hours. The interesting point are these peaks just before the hour, because I'm not no marathon runner, but marathon runners, they want to get in under the 4 hours. They want to get in under the 5 hours. So you put that extra effort in, so you get these huge, particularly at the 4 hours, this massive peak of runners coming in just before 4 hours so that they can say they did an under 4 hour marathon. Look at the difference. It's also men who tend to do this rather than women. There's quite a sexual bias on this. So that individual behaviour comes out in group behaviour as well. This is something that I struggle with in all my research: information decay. When patterns are laid down on the planet by various processes, they tend to be, reasonably clear, or they might be reasonably clear. But through time, that pattern becomes more eroded. And this is true about just about everything in the world. So I'm interested in the geological evidence behind how rivers changed in central Mexico. I'm collecting information on, or trying to collect data on things that happened millions of years ago, and that other processes have overridden that pattern. That pattern has been destroyed by erosion, etc., etc. So I'm dealing with a situation where I've got very patchy information about what happened in the past. But this is true for not just things like geological data. This is true if you're interested in, say, census information. We've got very good information from the present censuses. It gets less good as you go back further in time to the sort of 19th century and things like that. The quality of information. Some of the records might have been lost. Maybe they collected it in different manners. But there's an important thing, whenever you're dealing with temporal data, that you probably got this decay in information with time. Always bear it in mind. The world, this is a great book. I'd advise you reading if you're at all interested in the English landscape and how it came to be. This is probably the best book ever written on the subject. It's a bit old now, 1960s, I think it was written in maybe early 70s, but it's the story of how the English landscape was made. So here we're looking at, a sort of down, I don't know whether that's a down to probably scarp and fell topography. We've got a path running along the edge of this ridgeway. That path may have been used since prehistoric times. We've got enclosed fields down in the valley, maybe enclosed in the 18th century, 17th century as part of the Enclosure Act. Maybe this reservoir was dug in the Victorian period. But the landscape itself is the product of multiple processes happening in space and time at different times superimposed upon each other. And the word palimpsest comes from ancient Egyptian, the study of Egyptian scrolls, and it comes from the idea where you have these scrolls, and then you get people annotating these scrolls as time goes by. So you get multiple authors on the same document, and it's the same idea with a landscape. What you see, the landscape out there, is a product of multiple processes operating at different spatial and temporal scales. So whenever you look at a landscape, that landscape is a historical landscape. You may be just interested in the processes going on at the present day, but don't forget that how those processes are distributed over the landscape may have connections with what's happened previously in time. And I think this is the last one. Time travel. Okay, I mean, as far as we're concerned, it doesn't happen in reality, but you know, when you're thinking from a GIS and a database perspective, well, some people are interested in things like films and plots and how do we display, how would we use a GIS to display the plot, the spatiotemporal plot of a film or a story. These are all good uses of GIS. So, I don't know, recently we only just went past the day that they went to, didn't we? It was the Back to the Future day, it was about a month ago, I think. So, how would we incorporate potentially in a database the idea of time travel as well? It's not something most people would have to deal with, but it's potentially there as an issue for some users. So, that's my what is time, aspects of time, but ultimately it doesn't really matter. You know, that's, you know, it's good to think about. It's good to, I like to think about these things, but it doesn't really matter from an IT perspective. What is important is how time is measured, how accurate it is, what is, and what the, how we might measure time affects how we might store it, how we might analyze it, how much we understand the data that we have. Then, of course, there is the physical reality of how you represent time in the computer system, temporal data types, how we manage the change in spatial objects, the changes in relationships in objects and time, changes in database state through time, how we deal with uncertainty in time, and how we define temporal queries, spatiotemporal queries. You might be disappointed that I'm not actually going to give you definitive answers for these things. I'm as much going to identify a number of problems as to actually providing you with any particular solutions to problems. So I think we'll just, given that we're a bit late starting, we'll just do the measuring, maybe measuring time bit, and then have a little break. Okay, anybody know what that is? Nod the Mayan. Very close. It's the Aztec, actually. Just to be pedantic, it's the Aztec calendar. It's actually in Mexico, the Anthropological Museum in Mexico City. Well worth a visit. Amazing place. Okay, so how do we measure time? Well, most of the time we measure time with clocks. Some sort of clock, not surprisingly. Water clocks, that's a candle clock, Big Ben, devices that directly measure the passing of time. Sundials, you know, I'm not going to give you a list of all these devices. There's a whole load of devices that have been invented through time to effectively directly measure time. The other place we get information on time from is from proxies. Things that happen that leave a signature of time that we can then extract temporal information from. So here's an example, probably one you're reasonably familiar with, radiocarbon dating. So you're interested in how old an archaeological artifact is. You can get some carbon off it, maybe it's a bit of burnt bone or something like that. You measure the amount of carbon 13 to carbon 12, if I remember correctly. Is it 12 and 13 or 13 and 12 and 14? I can never remember which. It doesn't really matter, but you measure the ratio of two different carbon isotopes, and that allows you, because you know that the radioactive elements decay with a half-life, that half the radioactivity is going to decay in a certain period of time, we can take the amount of radioactivity and estimate how long ago that artifact was burnt or became into creation. This is actually this is actually a calibration curve rather than an actual sort of decay curve. This is a calibration curve. And why do we have to calibrate our radiocarbon dates? It's because the ratio of these isotopes of carbon, I believe, is dependent on temperature. So when it's warmer, the climate is warmer, you get a higher proportion of these isotopes, so you have to correct your time estimation on the basis of the temperature through history, and that's hence this calibration curve here. So we can get a direct measurement of, well, an indirect measurement of time. We can estimate time from things like radiocarbon dates, and there are many, many other proxies like this. There's obviously other isotopes for dealing with different dates. Potassium argon is used for sort of millions, up to sort of tens of millions of years of scale. Quite an interesting one that I know about is luminescence of sand grains can tell you how long they've been buried in the ground. So you can get an estimate of the date that the sand was deposited, say, in a lake bed, due to the amount of light that's been stored within a sand grain. It's incredible. Other proxies here, these are ammonites. I'm going to use a lot of biological examples because it's something I know about. So the different shapes of ammonites, the different species of ammonites are indicative of various temporal periods during, in this case, in the lower green sand, which is in the Cretaceous period. So we can identify and we can age the rock layers by the ammonite population that's found within it. So we've got two direct measurements of time and proxy measurements of time. So that's how we maybe measure time. But there are two types of time that we get out of that, two scales. We can have time on an interval scale, and I tend to call this absolute time. I don't know whether that's used by anybody else. And that is things like it's 12:23 on the 14th of May, 1657, or it's 12,500 years BP, before present. So that's giving us, on a continuous scale, we could have any time on that scale we liked, and it's an interval scale because it's got an arbitrary zero. If you're wondering what you should look up, if you're not familiar with scales of measurement, levels of measurement, then have a look at that. So you get ordinal, interval, ratio, and categorical scales. Okay, so if you're not familiar with those, have a look at those. So your arbitrary zero, well, 1657 is 1,657 years after this arbitrary point somewhere near the time when somebody died in the Middle East, so we think. So that has an arbitrary zero. Before present, well, that's an arbitrary zero. When is present? It's arbitrary. It's generally taken, I think, for be sort of roughly 1970, start the computer age. So we've got absolute scales, but we've also got temporal information on an ordinal scale. An ordinal scale is where you've got ordered units. Something is more than something else, less than something else. Ordered units. And I call this relative time. But relative time, I could appreciate, could be used for refer to other things. So things like before or after. This happened before this. This was causal to this, so it must have happened before. But also things like the geological and archaeological periods, the Neolithic, the Mesolithic, the Cretaceous, the Jurassic. These are the ordinal units, the Middle Ages, the modern period. The absolute scales require a zero and, an agreed, well, they don't require an agreed standard, but okay, so the absolute scale that you're most likely to come across is called UTC, Unit Coordinated Standard Time. And that is time in the modern period, okay? So it's Coordinated Universal Standard Time is run by the International Radio Consultative Committee and is basically the modern version of Greenwich Mean Time, which was abandoned in the 1970s, late 60s, 1970s, Greenwich Mean Time. And it's maintained by a weighted signal of several atomic clocks, including one just down the road at Teddington, I think. There's the National Physical Laboratory down there is one of the places that holds one of these atomic clocks that are used. It's not perfect. It's to do with the amount of the decay of radioactive isotopes, how often the decay occurs. But it doesn't match, to get it to match the rotation of the Earth, which is what we as humans think of as time. Occasionally we have to do things like add leap seconds to deal with the changes in the Earth's rotation. Otherwise our time will go out of step with the rotation of the Earth. And we're interested as much in the rotation of the Earth and its relationship to the Sun, and where, as we are in the actual, you know, how long, how many micromilliseconds is required for the difference. UTC, the accuracy of UTC is very accurate, and that's required to run the internet technologies, these incredible financial deals that go on in the present day on microfractions of a second. From a GIS perspective, always remember that time zones, the world is divided into time zones based on UTC, but those time zones are politically decided, and that, so depending on which time zone you're on, that there's an offset from UTC. So if you're wanting to, if you're comparing what's going on in Mexico to what's going on in the UK, do you want to know whether it's exactly happening exactly the same moment in time? So it's happening 6 a.m. At UTC, universal UTC plus 0, which is London, Greenwich, basically. Or, so do you want the equivalent time, which would be, what, 5 hours earlier in the, roughly in Mexico, which would be the equivalent of 1 o'clock in the morning, or are you comparing times of day? So just bear that in mind. Are you interested in the time in relation to, say, dawn and dusk, or are you interested in the absolute time, that's, so the same, exactly the same time, whether it's day or night in different parts of the planet?
Is there like a border, like is there a specific line in time? Like say if you, are they all over water? Like say if you just cross over and then...
Oh yeah, there are whole...
67 and then go back to...
Yeah. Certain countries, the US for example, is divided into 3 different time zones. East, west, central and west. So if you go over the border, you go over a state line and you've gone back an hour. Yeah, I mean, that's quite normal. If that's what you meant. Yeah. And of course, round the back of the world, in the inverse meridian, because he's roughly, you know, the back is roughly the inverse meridian, you lose a day or gain a day, depending when you go with the international date line. Here's an example of the ordinal scale, the international chronostratigraphic chart, the official sort of global geological scale. We know when the units start, the ages where the units start and finish. We know which ones are before each other, but if we've got something that's identified as being part of the Landinian phase, we know it's between 242 and 235 million years ago, but we don't actually know exactly when in that period it's used. There are lots and lots of different time scales that are implemented. Different interval scales, different ordinal scales. And just bear in mind that if you're dealing with historical data, then you've got to make sure that you're using the same scale. It's just like map projections. Think of them as analogous to map projections. These are projections of time. So two calendars, the Julian calendar and the Gregorian calendar. I can never remember. We're currently running on the Julian, no, the Gregorian. I get muddled up. But it doesn't really matter which. I think we use the Julian. But so here, depending, so if you're interested in historical dates, and some of them are recorded in the Gregorian and some are in the Julian, you can be up to 10, 11, even 12 days difference when you try and match those dates up. So bear in mind, I mean, for most modern data, this is irrelevant. It's in UTC, it's in whatever. But of course, you may be recording, if you're getting data from Mexico, it may be in local Mexican time. So it's kind of equivalent to that. So watch out for these scales, especially with historical data. And the fact that these different calendars or different scales are used in different places at different times across the planet. So if you're integrating temporal data, say on medieval agriculture across Europe, you might have to deal with the fact that some Italian province was still using the Gregorian calendar in the 17th century and things like this. All right, let's have a break, and then we'll get into the sort of more meaty part of the talk.